let H be Hilbert space, C subset of H, C is a closed in H, C is a convex subset. So as we have seen that there is a norm on inner product space arising from the inner product. If the space is complete with respect to this norm, then it is called as Hilbert space. That is, if it is every Cauchy sequence with respect to this norm arising from this inner product, if it is the case, every Cauchy sequence converges, then we say that such a space is what space? A Hilbert space. A Hilbert space is a complete inner product space. Inner product gives rise to a norm. Norm gives rise to, so norm is there, so you have sequences. So if every Cauchy sequence with respect to that norm converges, that is, if it is a complete metric space, then norm gives rise to the metric. If it is a complete metric space, then we say that it's a Hilbert space. So we have a Hilbert space. So it's a inner product space. There is a subset which is given to be closed and convex. So closed we know. What do you mean by a closed subset? A closed is that the complement of C. So suppose you have here over H, and suppose we have here over C is given to be. This is our subset C. Okay. So if you look at its complement, so this is the complementary space. So the complementary space, this outside space, the complementary space, if this is open, if C complement or H minus C, if this is an open set in the norm, okay, or the metric arising from the inner product, if it is an open set, the complement is open, then we say such a set is a closed set. The convex set, we have seen that. What do we mean by a convex set? Convex set is, if you take any 2 points in a convex set, you take a line joining that, then what does it becomes? So just like here, so if you take maybe say X and Y belonging to C, alpha belonging to the open interval 0, 1, then alpha X, or rather let's use the word T as to distinguish from the scalars. T belonging to, this is a real closed interval on R. Okay. Then what do we have? Tx plus 1 minus T y. If X and Y belongs to C, then for all T belonging to this thing should imply in C. So this is the condition. If this is the line joining X and Y, and clearly you can see that at T equal to, or rather what we can modify this thing as, we want a line joining X and Y, either this thing, or you can alternatively have 1 minus T X plus Ty belonging to C. So at T equal to 0, the value of this thing is X. At T equal to 1, this is Y. At T equal to 0, this is Y and X, the line joining Y and X, the line joining X and Y. So if for all X and Y, this is the definition of what? A convex set. So C is a closed and it is also what set? It's a convex set. So complement of C is open. H is given to be a complete metric space. So C is a closed convex set. So what happens here in this case is that if you take the infimum of the norms of the elements in C, then in fact there is an element which takes that infimum. So infimum is in fact a minimum. So what we are saying is that if we consider the set, so this is a proposition, what we want to, so C closed and convex subset of Hilbert space H, then there exists a vector in C of smallest norm. Okay, proof. So what do? We look at the following set. Let's call the set as maybe say H is there, C is there. Let's say tau. Tau is infimum of norm of X such that X is in C. Now note that there is a norm here. So tau is bounded below by 0. Also note that tau is a subset of R. In fact, R plus union 0. Tau is a subset of this thing. So tau is a norms of elements of C, or the vectors and so on. So it's bounded below, and hence what we can say is that if it is bounded below, it has an infimum. Okay, let a D be infimum of. So I would just I would erase here. I have already written here, so let me write here tau is equal to this. D is the infimum of this set, which is what tau, infimum of tau, or which is the same thing as the infimum of the set norm of X such that X belongs to C. So this is tau. Tau is a subset of R plus union 0. It is bounded 0. So here we have written infimum here. Tau, it was just a number here in this case. That is the reason I have taken. So D is the infimum. Now R is complete. So if R is complete, any subset which is bounded below has an infimum. So this infimum exists by the completeness property of the R. Okay, and hence what we can say is that D is existing as a real number. So there exists a sequence in R which converges. So because it is coming from this set tau, so there exists a sequence xn, n going from 1 to infinity in C such that norm of xn, this converges to D as a real number because the completeness axiom or the completeness property of the R. So what do we have? We have a xn as a sequence in C, and we have another sequence. What is another sequence? We have this norm x1, norm x2, norm x3, and so on, so on, so on. This is a sequence of non-negative reals. And it is given that this norm of xn, this converges to what? D. Okay. So norm xn, this converges to D. Xn is in C, norm xn is converging to D. Oh. So what we will show first, this is a convergent sequence. Convergence, this is in the norm, it is convergent. So we try to show that in fact this is also converging. So first, our first thing will show that the sequence xn, n going from 1 to infinity in C is Cauchy. This is our claim. Is Cauchy in C. Because if it is Cauchy, if we prove, then what do we have is that because it is Hilbert, every Cauchy sequence converges. Then we have the limit also. To show that this is a Cauchy, we will use the convexity property of C. So the convexity property of this, what does it allow? So T belonging to 0, 1. If you take any x and y, what should happen? 1 minus T x plus T y, this should belong to what? In C. If you x and y are any elements in C for t belong for any t, for all t and so on. So take t equal to half. So this implies that x half x plus half y, that is in C, or alternatively x plus y 2 belongs to C for all x and y belong to C. So one particular value of t are there, x and y are any, so this must belong to C. This is the definition of what? Convexity. Convexity. And hence what do we get is that we had the sequence xn, n going from 1 to infinity in C, whose norms were converging to D. So what do we have is that if you take any element from here, maybe say x5 and x10, then x5 plus x10. So if suppose xr and xs is there in the sequence and going from 1 to infinity, then xr plus xs divided by 2 also belong to C, because these are elements in the sequence and this sequence is in C, is a subset. So for any, if you take add and you divide by 2, so the scalar half multiple of this thing, that is in C of this sequence. So what does this give? So we have, let's take maybe say xm and xn of the sequence, that is also in C. So what would happen to the norm? So xm plus xn divided by 2, we take this thing. Look at the norm of this object. The norm of this object, because this object belongs to C and D is the infimum of the norms of elements of C, this is always greater than equal to D. The norm of xm plus xn is always greater than equal to 2D. So norm of xm plus xn norm is what? Greater than equal to, the square of this thing is 4D square. So we have this thing. Use the parallelogram law. So what do we have? Parallelogram law, norm of xm plus xn whole square plus norm of xm minus xn whole square. This is equal to 2 times norm of xm whole square plus 2 times norm of xn whole square. So shifting this on the right hand side, norm of xm minus xn whole square, this is equal to 2 times norm xm whole square plus 2 times norm xn whole square minus norm of xm plus xn whole square. So what do we get from here? This is greater than equal to the term over here. So if you have this is greater than equal to this thing, what also can be written, multiplying by minus sign, it changes. So norm of minus norm of xn plus xn whole square is less than equal to minus 4D square. So this object, so what would happen, is less than equal to, so because it is a negative sign, so this term as it is, so less than equal to 2 norm xm whole square plus 2 norm xn whole square minus 4D square. What is here? Norm of xm minus xn whole square. So this is what we have got. But xn, what do we have? Xn is the sequence and norm of xn is converging a norm of xn. So so given epsilon, there exists a stage. So we as this sequence, this as a sequence and going from 1 to infinity, this converges to D. So as n tends to infinity, so this goes to D, this goes to D. In other words, norm of xn minus xn whole square. What would happen? This is less than equal to, so this is 2D as n tends to infinity minus 4D square, which is 0. But this is a norm, so it is always bounded by below by 0. So this is bounded by 0. So in fact, what do we get? From here we get that that in fact, so it's a Cauchy sequence. A more proper way to do this thing is that so more proper way would be what, given epsilon, there exists a stage n1 such that after that stage, so there is, as n tends to infinity means certainly there is a, and so you can write an epsilon argument over here. So after that finite stage, any m and n you take, their distance is less than epsilon. So in fact, it's a Cauchy sequence. It's a Cauchy sequence in C, and C is a subset of H, and C is a closed subset of H. Closed subset of complete metric spaces this is R complete. This is a fact what we have proved earlier in metric spaces. So closed subspace, so C itself is a what space is a complete, so it's a Cauchy sequence in C. So there exists a what X belonging to C such that this sequence Xn converges to C, converges to what X, and we have already seen that norm of Xn which is converging to D. So norm of X is clearly what? One can easily see that norm is in fact what? Norm of X is equal to D, because norm Xn converges to D. Right. Now we have proved the existence of the limit, okay, and so on. The norm of X is the, maybe if it is converging to some other limit also. So what we are saying is that we have found an object in C which is the element, which is the infimum of the norms of the elements of the C. So we have found an element of the least norm, and what we want to claim further is that such a element or such a vector is unique. Further, as a corollary, if you want. So suppose there are two vectors x and x dash in the C, and both of them have norm D. That is, they are the element of the vector of the least norm. Norm of x dash, that is also D. Again, x plus x dash, this argument by 2, this is in C. We use again parallelogram law is what? X plus x dash whole square plus norm of x minus x dash whole square 2 times norm of x whole square plus 2 times norm of x dash whole square. We divide by 4 throughout this equation. If you divide by 4, then what do we get? Over here is 2, and 4 square is what? X plus x dash divided by 2 whole square, because 4 is a real number, and if you try to, it's a non-negative real number, so you can bring inside the norm, and 2 square is what? 4. Norm of x minus x dash 2 whole square, and here it would be dividing 2 divided by 4 is 1 by 4, so norm of x square divided by 2 and norm of x dash whole square divided by 2. So norm of x plus x dash divided by 2, this is equal to what? Norm of x whole square divided by 2 plus norm of x dash square divided by 2 minus norm of x minus x dash by 2 whole square. Now if you look at this square plus this square, so these terms are all non-negative, these two terms, here you are subtracting, so this is less than equal to just this term, norm of x divided by 2 norm of x dash whole square divided by 2. Now this object is d square divided by 2, d square divided by 2. So what do we get is that this term over here, the argument is that norm of x plus x dash divided by 2 whole square, this term is what? Is in fact less than equal to d square by 2 plus d square divided by 2, which is d square. So norm of x plus x dash divided by 2 whole square is in fact what? Strictly less than. Why it is strictly less? Yes, less than equal to, we are subtracting this thing, yeah. So norm of x is d square, and x minus x dash divided by 2 is in fact why it is strictly less than, we can just remove the less than equal to symbol also. The point is that we are assuming, so let's write, so since we are assuming what? X is not equal to x dash, since over here x is not equal to x dash, so this term over here will not be 0. So if it is not 0 means what? It is strictly some positive real number. So when you subtract some positive real number from a non-negative real number, so you have a strict. So this is strict. So this is strictly smaller than what? Strictly smaller than d square. But because it is a convex set, x and x dash belong to C. So x plus x dash, half of this thing, this belongs to C because of the convexity. So we have found an element whose norm is even smaller than the smallest norm which can exist on C. So which is a contradiction. If it is a contradiction, and hence what we have shown is that why this contradiction is arising, because we are assuming that x is not equal to x dash and hence x is equal to x dash. So we have found an element of the smallest norm. So if C is a closed convex subset of a Hilbert space H, there exists an element which is unique of smallest norm.